Now for something completely different. So we're switching gears. I'm switching gears. I'm not going to talk about combustion so much. I'm going back to computer science in my last part here to talk about some unsupervised machine learning methods, primarily for anomaly detection in scientific data using joint statistical moments. And this is work that I didn't do, but my postdoc and others at Sandia worked on for a number of years through support from the DOE Advanced Scientific Computing Research Office. Combustion here was used as a use case to help develop this method. And so I just showed you this reheat combustion problem, and it's characteristic of all the large-scale hero runs that we're generating, and lots of others are generating. The attributes of these calculations are that we're transporting tens to hundreds of variables. It covers several decades in scales, from the turbulence as well down to the flame scales, ignition scales. And the DNS simulations generate high-resolution data and that are well-resolved with smoothly varying functions. So this might be a different scenario if you have experiments with noise or incomplete data or gappy data that you were trying to fuse with numerical simulations. But for the moment, let's concentrate just on having smooth data that's well resolved. And I think someone had just come up and asked me how expensive are these DNS calculations. That in terms of CPU hours, they consume about tens of millions of CPU hours per run. And just trying to get a ballpark idea, some of these computer centers that are with the hardware costing upwards over $100 million, and that are transitioned every few years, every 3 to 4 years, and associated operating costs with power, cooling, and staff, I would guess that these calculations are over $1 million. And so they're expensive hero runs, and I think that they generate large amounts of data on the order of hundreds of terabytes of data that are currently stored. That's a problem in and of itself. We want to make sure in the future that we can move more of our analysis to the extent that we know what we're going to analyze in situ, so that just like in an experiment, you don't save every data, but you just go back and rerun a case. Here we want to extract as much knowledge and analysis on the fly as we can to prevent having to have these humongous storage systems. Okay, now this is what happened yesterday when the thing went blank, so unplug it and plug it in. Okay, we're back. So, so in addition to computing or costing a lot to simulate and large amounts of data to store, and I think, and these, as I said yesterday, the way to get to exascale is through large concurrency, millions to billions of processors. We have to have efficient workflows. And in CFD and in combustion especially, a typical workflow might look like this, this diagram, where you first do the initialization, and then set up your mesh, construct the various terms in your governing conservation equations for momentum, energy, species transport, update the solution, and then rinse and repeat this time advancement loop until you're done. Now, when you start to add more complex numerical methods that are required, like adaptive mesh refinement, and if you start to include in situ analytics, like the SEMA analysis or flame element tracking, Lagrangian sprays, all kinds of stuff, machine learning methods, including what I'm going to talk about now, then you have more complexities that are going to happen. But you'd like to have, and then also we want to save data less frequently. You can't afford to save petabytes of data because you'll fill up the storage device at these supercomputers pretty quickly. And so in order to steer these boxes in green, for example, adaptive mesh refinement, downstream analysis or adaptive I/O, we need some metrics to tell us when and where in these simulations to do it. And a lot of the phenomena I've been describing in these lectures have to do with intermittent phenomena like autoignition. I didn't talk about extinction. But there could be a lot of utility in using developing anomaly detection methods. And the ones that are available to the computer science community right now include things like K nearest neighbors, which computes the mean distance from K nearest neighbors based on a selected threshold, local outlier factor, which computes the outlier score based on some density metrics, or supervised machine learning methods such as neural networks and various other regression, both linear, nonlinear, and classification methods. However, a lot of these existing methods are not efficient and are expensive to compute. So the idea that Aditya had was to consider higher order moments. And so he constructed some synthetic data. He took a bivariate data set and characterized, with normal data shown by the scatter points on the left for these two variables, V1 and V2. And then he took a few data points out of this, this data on the left and put them way out here along the V2 axis, which is what he's calling anomalous data, so data with anomaly present. And so the question is whether we could characterize the data distribution based on ideas we already know about, like principal component analysis. And to detect the anomaly, you have to detect some change in the distribution. And in particular, the effects of changes in the magnitude of the principal value and orientation of the principal vectors from the PCA analysis. And so with PCA analysis, the first step is to typically scale the data. And so you want to subtract out the mean and then normalize, divide by the maximum values. And then typically you compute the covariance matrix based on the second order joint moment. And then you perform an eigen decomposition to get the values of the principal values and their vectors. And so if we plot the first principal vector and the orthonormal second principal vector on top of this synthetic data, you can see, well, the principal vector, first principal vector aligns with the scatter or variance in the data as you would expect from this analysis. And the second vector is orthonormal to that. If we then apply the same PCA analysis to the data with the little bit of anomaly in the corner, we see that indeed the principal values themselves change a little bit. It's 0.21 and 0.016 here, and it changes a bit on the right, but the direction of the vector doesn't really change. And so the current PCA analysis that we all do captures the variance extremely well, but it does not capture changes that we would need to detect anomalies. So we have the idea to take a look at using higher order moments to capture these extreme events. So one higher order moment, the kurtosis, is a good measure of existing outliers according to Westphal, and the propensity to produce outliers for situations like autoignition or local extinction or detonations that are forming sporadically, or even the underlying turbulence field itself, the intermittency with the scalar dissipation rate, for example. So analogous to PCA that we normally do, here we have to construct the fourth co-kurtosis joint moment, which is a cumulant tensor. And then we have to decompose this fourth order symmetric tensor, which scales as the number of features to the fourth power. So this is a large tensor. To decompose it so that it's possible to use, we matricize the tensor and perform a singular value decomposition. And from that, we can obtain the principal values and their vectors, the kurtosis vectors. So if we take that same synthetic data and we plot the principal kurtosis vector, PV1 shown in blue, I don't know why my pointer doesn't work. Well, oh, there it is for a second. There it is. You can see that the kurtosis vector aligns well in the direction of the anomalies. And again, you have the second, whereas the original second moment principal vector aligns with the variance but not the anomalies. And so there's a glimmer of hope that we might be able to use this to characterize extreme events. So we took a little bit more realistic case. This is still synthetic. It's a combustion test case with autoignition. And we basically defined in one dimension a spectrum of temperatures. And we decomposed it into, let's say, 4 domains, computational domains, regions 1 through 4. And deliberately imposed a higher temperature of 1600 in only the first domain. This happened to be a mixture for hydrogen, it was hydrogen CO, syngas mixture. And we looked at the evolution with our DNS code S3D. The number of the time steps here were very, very small, on the order of fractions of a microsecond. And we dumped out about 20 checkpoint files at intervals of about 1 microsecond. So the autoignition solution here is trivial. What you see in time is that the first region on the left autoignites first because the temperature is hottest there. So you can see the temperature goes up rapidly to well over 2500 in the first domain. And then the rest of the domains 2, 3, and 4 also autoignite, but at later times. And it ignites in the order of domain 1, region 4, followed by region 2, followed by region 3. And so we want to see if we can detect the early ignition in region 1, which we're calling our spatial anomaly. And then eventually, as I said, this ignites in the other regions too. So we computed the co-kurtosis principal vectors in region 1. Again, the axes are scaled. And we see at time 0, the alignment of the vector is only with temperature because nothing has reacted at that point in time. But as time progresses, I should say we're plotting temperature versus mass fraction of H2. But as you can see, as time progresses, that vector rotates and tracks the evolution of that first ignition kernel in region 1. As the temperature goes up, some of the fuel is consumed. And so the vector actually rotates into mass fractions for hydrogen. And I'm not sure why Aditya plotted negative values, but in any case, it represents some weird normalization, but it represents the consumption of H2. So the vector rotates from only temperature towards co-kurtosis that is got some balance between temperature and mass fraction, but it's able to capture the change. The co-kurtosis, the principal vector is denoted by the solid colored lines. So the next thing that Aditya looked at was defining feature moment metrics that project these vectors from the co-kurtosis tensor weighted by their principal values onto the features to obtain the so-called feature moment metrics. And the number of features for this simple example is 13 with 12 species plus temperature. And the number of subdomains here, as I said before, is 4. And so once we have the feature moment metrics, then we can see how the feature moments distribute across the different features when, as the ignition anomaly occurs. And so if we look at the 4 regions that are color-coded, we can see their evolution in time by going across the top row and then the second bottom row. So initially, all of the features are only aligned with temperature, where we've added the temperature fluctuations to the solution. But a short time later, we see some of the feature moment metric is distributed in region 1, as denoted by red color, into these other features, these other species variables that become important during autoignition. Subsequently, later in time, regions 4, followed by regions 2 and 3, also distribute their feature moment metrics distribute across different features as well, until at much later time, you see all of the 4 regions are undergoing different degrees of autoignition, and the feature moments are distributed among the various species and temperature. So then how do we define an anomaly metrics out of the feature moment metric? And in particular, the statistical signature for this is to see how the feature moment metrics change, the distribution of the feature moment metrics change, either spatially at a given time or temporally, if you're just tracking a given feature as it evolves in time. And so what we're using to define this is the Hellinger distance, which is a symmetric measure of the difference between 2 different discrete distributions of P and Q. And the value of this metric is 0 when there's no change, and it's unity when 2 quantities are complementary. And so we applied this Hellinger distance and developed a spatial metric based on the feature moment metric distribution with respect to the average in the computational domain at a given time. Likewise, complementing that, we also developed a temporal metric which compares the feature moment metric distribution between successive time steps. And so the basic numerical algorithm that we added, we first did this in a post-processing loop, and since then we're adding this as an in situ method so we can detect these anomalies as the simulation progresses. And so basically we decompose the data into the various domain decompositions. We select the features, and then over a time loop, we scale the data, and we compute the joint moment tensor. We matricize the tensor, perform the singular value decomposition to get the eigenvector and the eigenvalues, and then we compute the feature moment metric, as I just described, and using the Hellinger distance. And so we just repeat that and use that to flag anomalous subdomains. So the results of this are shown here for the simple 1D problem, where the dashed line is a threshold for anomaly that we arbitrarily selected to be 0.5. And I'll talk about the sensitivity of that selection in a minute. And again, the 4 regions, region 1 ignited first, followed by regions 4, 2, and 3, as color-coded by red, purple, green, and blue. And so you can see the spatial metric develops in the anomalies are detected both from the spatial metric as well as from the time metric. And you can see, indeed, the anomalies detected first in the spatial metric for region 1, followed by regions 4 in purple, regions 2 in green, and regions 3 in blue. And so this was indeed what happened in the DNS as well. And also, you can see that the time metric was even more sensitive than the spatial metric in detecting that anomaly of the first region to autoignite. And so in this case, the time metric might have been more useful than the spatial metric. So then we moved on from the synthetic data and took one of our 2D homogeneous charge autoignition data sets for premixed ethanol air with EGR dilution in 2D that Ankit Bhagatwala had simulated earlier. And so this was a constant volume situation where we had temperature fluctuations about a mean temperature, and it was being stirred by 2D turbulence at high pressure and a constant volume, and then autoignition progresses. So the mean temperature in this case was 924 degrees Kelvin with the fluctuation in the temperature of 40 degrees Kelvin. And we subdivided this computational domain into 144 subdomains, and then we computed the anomaly detection on this data. So this is what happened when we evaluated the anomaly detection algorithm to detect, again here, the earliest inception of ignition. So you can imagine that this might be a very useful algorithm to include for looking at DDT or knock, engine knock, right? You might want to use something like this to detect incipient formation of knock in an engine. And so the actual true heat release rate shown in these 144 domains is this image on the top left. And then using the detection methods in space and in time, M1 and M2, this is what you get for each of the subdomains. And so the true events of autoignition are detected in these subdomains, whereas the predicted events from this anomaly detection algorithm are given by these red filled-in boxes here and here. And so there is some error still in the algorithm. It probably depends on the threshold values that you select, but statistically we found that we got the correct solution well over 90% of the time with a few bad solutions, a few false solutions along the way. We did also look at the performance of the algorithm in terms of the threshold value that you choose. So when you choose a higher threshold value for the heat release rate, then your region of interest shrinks, and the overall method becomes more accurate. And so that's measured by this curve plot called the receiver operating characteristic, ROC curve. And indeed, when we see many improved true positive rates as we increase the heat release threshold. So we're at the stage now where I think we're going to test this anomaly detection in some of the 3D cases that I presented earlier today for both the temporal endodecane turbulent autoignition as well as for the multi-injection two-stage ignition problems to see if it can detect some of the anomalies. But I think it looks to be a very promising method. And we verified the idea using both synthetic and some 2D autoignition data. And we're in the process of working with some of the computer scientists to figure out how to implement this algorithm in situ or on the fly in both S3D as well as in some of the AMR codes. And we'll need to evaluate the scalability of the algorithm. Things like the evaluation of the streaming singular value decomposition for the eigen solution need to be made very scalable. And then if this all works, then we want to apply the algorithm to detect anomalies in other science phenomena as well. So that's all I have. But I wanted to just give you an idea of the kinds of unsupervised machine learning methods that can be useful to detecting intermittent events in CFD. So that concludes what I have to say. I'm sure you guys have questions. Yes.
So I believe that since we are calculating SVD, that's a pretty expensive, computationally very expensive since we are calculating eigenvalues and eigenvectors. So I know this is probably a very preliminary study for now, but do you think it would be worth it to try this on a 3D case rather than maybe just have a visual inspection? Like someone, so
So are you talking about using just kind of pattern recognition
No,
from an image recognition?
something like that, because the trade-off would be pretty high in terms of computation power.
Right. We haven't thought about, I mean, they're kind of two completely different methods, right? What we are trying to do is to apply this method to a fully 3D turbulent auto-ignition problem first to see what its success rate there is, and maybe it'll identify other problems. And then you're right, there's room for a lot of CS and applied math help in trying to find more efficient ways to do the eigen solution on the fly, and maybe through some kind of streaming methods. And these CS guys are wizards at matrix multiplies, right, and linear algebra. So I'm hoping that we'll get some answers from them.
Thank you.
Yeah.
Probably we'll save the answers, questions afterwards.
Okay.
Thank you.
Thank you.